This is mixed exercise 6.02 on projectiles, A-level applied maths, year 2 mechanics. We're going to answer two questions. Question 1. The points A and B lie 40 meters apart on a horizontal ground. At time t equals to 0, the particle Q and R are projected in the vertical plane containing A, B, and move freely under gravity. Particle Q is projected from A with speed q meters per second at an angle alpha to AB. And particle R is projected from B with speed 30 meters per second at an angle 60 degrees to BA, as shown in the diagram. At time t equals to 2 seconds, Q and R collide. A. Find the size of angle alpha and the value of Q. B. Find the speed of R at the instant before it collides with R. So I'm going to use vectors. So for particle R, the initial velocity in vector form will be given by U, I will denote it by R, will be equals to 30 cos 60, that's the horizontal component, and 30 sine 60 vertical component. If you simplify that, you're going to get 15 and 15 root 3 meters per second. I'm going to consider upward direction to be positive and downward direction to be negative. And so that means that my acceleration, which is also a vector, will be given by 0 for horizontal and minus 9.8 for vertical meters per second squared. Now I'm going to use the Stewart equation S equals to ut plus half at squared in vector form. So S will be a vector, U will be a vector, and A will be a vector. So when t is 2, so when t equals to 2, I have S to be xy in meters. So this equation becomes xy will be equals to 15 and 15 root 3 times 2 plus half, my acceleration will be 0 minus 9.8 times 2 squared, which is 4. If I simplify that, I'm going to get xy equals to 30 and 30 root 3 plus 0 over here and minus 98 over 5 for the vertical component. This will reduce to 30 for horizontal and then 30 root 3 minus 98 over 5 for the vertical component. So now for particle Q. So for particle Q, the initial velocity, which I'll call UQ, will be given by Q cos alpha and Q sine alpha. Again, our acceleration will be given by 0 minus 9.8 meters per second squared, just like the first one. And when t equals to 2, we have the following equation. So when t is 2, and using the same equation here, the position vector will be given by xy equals to q cos alpha and q sine alpha times 2 plus half brackets 0 and minus 9.8, all of that times 4. So this will simplify to 2q cos alpha and 2q sine alpha minus 98/5, all in vector form. At this point, we go back to diagram and try to do some illustration. So when Q is projected, the path might be something like this. And then the path of Q might also be something like this. So they'll meet over here at this point. Now at this point, they are at the same vertical height, which I can label as y, so I can call that y, which will be the respective y components that we got over here and over there. So at this point, we also know the respective distances of Q from A and of R from B. And these are given by the horizontal components of the vectors. So that for R will be 30, and that for Q will be 2Q cos alpha. So we can put that on the diagram. So this distance here will be 2Q cos alpha, and this distance here will be, this component here will be 30 meters. But we know that this plus that will be 40, so we can write that equation down. So we can now say 2Q cos alpha plus 30 will give us 40. That means 2Q cos alpha is equals to 40 minus 30, that would be 10. If I divide everything by 2, I'm going to get Q cos alpha is equals to 5. And as we've discussed before, this length here for both of them is the same. So we can equate the y component of the vectors. So it means that this is equal to that one here. So I have 2Q sine alpha minus 98/5 will be equals to 30 root 3 minus 98/5. So as you can see, this will cancel with that, and the equation reduced to 2Q sine alpha equals to 30 root 3, which also means that Q sine alpha is equals to 15 root 3. So I've got two equations that I can solve simultaneously. This is equation 1 and then equation 2. So I'm going to solve those two simultaneously. And so I can have Q sine alpha divided by Q cos alpha will be equals to 15 root 3/5 over here. So I have 15 root 3/5. So this and that can cancel, and then I have 5 here goes 1 and 5 goes to 3, and so I have tan alpha is equals to 3 root 3. That means alpha is equals to tan inverse of 3 root 3. and that will give me alpha equals to 79 degrees. And so that's the value for the alpha. For Q, what I can do here is square equation 1 and equation 2. So if I do that, I'm going to get Q squared cos squared alpha plus Q squared sine squared alpha is equals to 5 squared plus 15 root 3 all squared. Then I can get Q squared brackets cos squared alpha plus sine squared alpha equals to 25 plus 6, 7, 5. Well, cos squared alpha plus sine squared alpha equals to 1. And so the left-hand side of the equation becomes Q squared is equals to 675 plus 25 is equals to 700. And that means that Q is equals to square root of 700, which is the same as 10 root 7. And so Q is equals to 10 root 7 meters per second, or 26.5 meters per second. And that's the answer for second part of A. So for B, we are going to find the speed of R at the instant before it collides with Q. So I'm going to use another two-vector equation. This time it's going to be V equals to U plus AT in the vector form. So V is a vector, U is a vector, A is a vector, and T is the only scalar over there. At the instant that it collides, the value of T is 2. The acceleration due to gravity is still 0 minus 9.8 in the vector form, and U is 15 and 15 root 3. So if you do the substitution, I'm going to get V is equals to 15 and 15 root 3 plus 0 and minus 9.8 times 2. If I evaluate that, I'm going to get V is equals to, in vector form, 15 and 15 root 3 minus 19.8 meters per second. This will simplify to 15 and 6.18 meters per second. But I want the speed. The speed is the modulus of the vector V. So that will be the same as square root of 15 squared plus 16.1 squared. So we are finding the magnitude of this vector here. And then if you evaluate that, you're going to get 16.2 meters per second. And so that's the speed of R at the instant it collides with Q. Question 2. A boy kicks a football on a horizontal ground towards a fence which is 10 meters away. The ball moves in a vertical plane which is perpendicular to the fence. The ball just passes over the top of the fence, which is 2 meters above the ground, as shown in the diagram. The ball is modeled as a particle projected with initial speed u meters per second from point O on the ground at an angle of alpha to the ground. A. by writing down expressions for the horizontal and the vertical distances from O of the ball t seconds after it was hit. Show that 2 is equal to 10 tan alpha minus 50g over u squared cos squared alpha. For B, given that alpha is equal to 45, find the speed of the ball as it passes over the fence. So I'm going to use vectors again in this question. So the initial velocity of the ball, u, in vector form is u cos alpha for the horizontal component and u sine alpha for the vertical component. And this is meters per second. We are taking upward direction to be positive and downward direction to be negative. So our acceleration, which is also in vector form, will be equals to 0 and minus g meters per second squared. At this point here, this point has components 10 and 2 because this distance from O is 10 meters as stated in the question. So that means the position vector of this can be written as S equals to 10, 2 meters. So now using the Sylvert equation, S equals to ut plus half at squared in vector form again, I can do my substitution to get the following. 10, 2 equals to u cos alpha, u sine alpha times t plus half brackets 0 minus g t squared. This will simplify to ut cos alpha, and for the vertical component you have ut sine alpha minus half g t squared. So we can see that for the horizontal component we can have 10 equals to ut cos alpha, which implies that t is equals to 10 over u cos alpha. For the y component, we have 2 is equals to ut sine alpha minus half g t squared. Now I'm going to substitute the value of t here into this equation here. And if I do that, I'm going to get 2 on the left-hand side. And on the right-hand side, I'm going to get u times the t, which is 10 over u cos alpha times sine alpha minus half g, and my t be 10 over u cos alpha, all of that squared. I can now see that this u will cancel the u, and the whole equation will now be reduced to 2 equals to 10 sine alpha over cos alpha minus 100 g over 2 u squared cos squared alpha. Now, sine alpha over cos alpha is tan alpha. I can also see that 2 can cancel here 1 and 2 can cancel 150. And so the equation now becomes 2 is equal to 10 tan alpha minus 50g over u squared cos squared alpha. And that is the proof required. So for B, this question can easily be solved using energy principles. So those of you doing further math, you can go ahead and use energy principles to solve this. But this video is being made for students of A-level maths and not A-level further maths. So I'm not going to use energy principle to solve this question. I'm going to use an alternative method. So when alpha is equal to 45 degrees, then using this equation here to obtain the value of u, we can have 2 is equals to 10 tan 45 minus 50 g all over u squared cos squared 45. That will be the same as 2 is equals to 10, because tan 45 is 1, and that will be minus 50 g over u squared. And cos 45 is root 2 on 2, so that will be root 2 on 2 all squared. I'm going to simplify this equation and rearrange. And if I do that, I'm going to get 50 g over u squared times a half is equals to 8. Because 10 minus 2 is 8. Now I can multiply 8 by half, and that will give me 50 g over u squared is equals to 4. So I can solve for u now. U squared is equals to 50 g over 4, which is also the same as 25 g over 2. So that's u squared. So u will be equal to square root of 25 g over 2. I'm now going to use the value of u to find the horizontal component of u, which is here, u cos alpha. So if I call that ux, that will be equal to square root of 25 g over 2 times cos 45. So ux will be equals to square root of 25 g over 2 times, and cos 45 is 1 over root 2. And if I evaluate that, I'm going to get 5 root g over 2. So at this point, I'm going to indicate it on the graph. So that is the horizontal component of the speed, and it will be indicated on the graph like that. So we can label that as ux, which is equals to 5g over 2. We now need to find the vertical component, which will be like this, coming down. And then if I call that Vy, I can now evaluate the value for Vy. And I'm going to use another Seward equation. And this time, it's going to be V squared is equals to U squared plus 2AS. So we are going to consider the vertical direction. And using this equation, the value of Vy will be given by Vy squared is equals to U squared sine squared 45 minus 2 times g times 2, because g is negative coming down this direction. So I'm going to simplify that. I know u squared. I can find sin squared 45. And so that will give me u squared we got as 25g over 2. And so I have 25g over 2 times, and sine 45 is 1 over root 2. So 1 over root 2 squared is a half minus 4g. So this will simplify to 25g over 4 minus 4g, which is equal to 9g over 4. So it means that Vy will be equal to square root of 9g over 4, which is the same as 3 root g over 2. Now this is the y component, Vy. So now I can put this on the diagram. So Vy now is equal to 3 root g over 2. So we are required to find the speed. So if I say speed is equal to v, and v as shown on the diagram will be the resultant of this vector and this vector. And this will be something like this. So that is v. So we can use Pythagoras theorem now to find the value of v, which will be the square root of this squared and that squared. So the required speed, v, is equal to the square root of this squared, which is 25g over 4, plus the squared, which is 9g over 4. So v is equal to the square root of 17g over 2. And if I evaluate this, I'm going to get v is equal to 9.1 meters per second. And this is the required speed. And this brings us to the end of this session on projectiles, mixed exercise 6.02, A-level applied maths. Thank you again for watching. See you in the next video.